In the previous video, we have learned that the main statistics that characterize distribution of your qualitative variable, it's a proportion. So you have different categories, and then every category has its proportion, and that gives you a distribution that you can visualize, for example, using a bar plot. However, proportion for one particular category is a statistic. So it means that if you take another sample, even of the same size, even from the same population, the proportion that you will get for this particular category will be different. So it varies randomly as any other sampling statistic. In this video, we will learn how to make an inference on proportion, and let me remind you what inference is. Inference, it's the way to generalize knowledge that you gain about your sample, for example, computed different statistics, right, to the whole population. So that's the inference. And you can make an inference using two different ways. You can either compute confidence interval for the corresponding population parameter, so in this case it's a population proportion, right? Or you can make a test assuming that population proportion is known. So I'll show you both. But first of all, let me remind you that we usually use Greek letters for population parameters in this course at least, and we use the Latin letters for sample statistics. I will follow this notation. In this case, I will use pi for proportion of population and p hat for proportion of a sample. Well, first of all, why p hat? Why not just p? It's just to avoid confusion, avoid that you mix the proportion with a p-value. So that's why I call it p hat. And then pi, you remember that we also use pi as a power of test, but I hope it will be easy not to mix it because we are not going to talk about power of test in this particular video. So when you see pi in this learning sequence, it means a proportion of a population. And then if you use p hat, if you see p hat, it means it's a proportion of your sample. Okay, so it's observed proportion. And then I must say that making inference for proportion, it's not that easy. There are many different ways to do that, because you can describe behavior of proportion using different distributions and also computing different parameters of this distribution. For example, in this paper, you will find out, if you Google and try to read this paper, you will find out 7 different methods to make an inference. And then you will find out some of them are a little bit more robust, some of them are less robust. However, I'll show you the simplest method because it's easy to understand, also based on what you have learned so far. This simple method works well if your proportion is not too small and not too large. For example, if your proportion is between 0.20 and 0.80, then this method works really, really well. But if your proportion is smaller, for example, 0.01 and 0.99, you need either really, really big sample size or you need to use another method. So therefore, let's learn how this simple method works. So we will learn everything based on the simple method, but if you want to use a little bit more robust method, a little bit more reliable method, simply use a software. It's very rarely you compute your statistics manually. For example, prop test, it's a function in R that computes confidence intervals and make a proportion test, provides you one of these more reliable methods. Okay, but the theory I will explain using a simple method. So the simple method is as follows. The proportion of your sample varies randomly around the proportion of your population, and this distribution of the proportion of your sample around proportion of your population is normal distribution. So you can use normal distribution in this case under certain requirements which we'll discuss later. The standard error, which is standard deviation, right, for statistic for proportion, is this one. So you can compute standard error of the sample proportion if you know the population proportion. Okay. So this is sample proportion, this is population proportion, and then of course you know the sample size as well, and this is just repeating what I have said. So the proportion of your sample is almost normally distributed around proportion of your population. And then the parameters of this distribution, the average is proportion of your population, and the variance, what you have under the square root, it's simply you take a proportion of your population, then you take for example, if this is McDonald's, this is all items, the proportion of students who didn't select the McDonald's, right, in the population. And this is the sample size. Okay, so this is the variance. Now, this will work only if you have at least 5 items both in the category you're testing and in the other categories. So what it means, for example, if you test a proportion of people who selected, I don't know, who use iPhone instead of Android, so you need to have at least 5 people who selected iPhone and 5 people who selected something else like Android, for example, right? So this is important requirement. Otherwise, you cannot use normal distribution in this case. Usually people use even larger values like 10 or 15, but 5 actually, that will work as well. Okay. Now, what you can use this knowledge for? Strictly speaking, because both variance and average of this distribution depends on the population proportion, you can use it only for one thing. You can compute expected proportion of your sample. Not very useful because usually we don't know proportion of our population, but let's start with this simple example. So if you know proportion of population, and if we are going to select a sample from this population, we can predict parameters, we can predict characteristics of this sample. Let me show you a couple of examples. Let's say this is the true data. According to survey from 2022, approximately 30% of adult people in Denmark have higher education. Now, we are going to make a survey, and we are going to select 1,000 adults all over the country, accounting for size of cities, so it will be a really unbiased random sample, so sample should be good enough. How many of them will have higher education? So how many of these 1,000 adults will have higher education in our sample? So that's, for example, we can compute using this knowledge. So we know that the sample proportion, this is what we are looking for, is distributed randomly around population proportion, and we know that this distribution is normal. So that's enough. Now we know the proportion of population, we know the sample size, and then we can compute the variance. You can see that this is the proportion of population, and this is 1 minus proportion of the population divided to the sample size. So this is the variance. Then we can compute the standard deviation just by taking the square root of the variance. And after that, we need to decide at which confidence level we should work. Of course, you need to decide it before, right? So you need to decide it when you plan your experiment. But let me show you just 2 examples. If you work at confidence level 95%, you know that to get 95% interval in normal distribution, you should take 1.96 standard deviations or standard errors in our case, right? So it means that z-score is minus 196 for the left side of the interval and plus 196 for the right side of the interval. Now we can compute the error margin, the length of this interval, by taking absolute z-score, 196, and multiply to the standard error. So we compute this part, right? And this is 0.027 or 2.7%. Now we take it, we subtract it from the proportion of population to get the left boundary, we add it to get the right boundary, and that's the expected values. So with 95% confidence, so we have 95% chance that when we take a sample of size 1000, when we ask 1000 randomly selected persons, the number of the people with high education will be between 273 and 327 in this particular case. Okay. Of course, we have 5% chance that it will be outside this. And then if you, for example, work with 99% confidence level, then your z-score will be a little bit larger. It's 2.58 minus for left boundary plus for right boundary. But the idea is the same. Now you compute error margin. You can see it's also a bit larger, 3.6%. And then you subtract or add this error margin to proportion of your population. And that gives you the interval, which means that if you work with 99% confidence, so you have 99% chance to get a sample. And if this is true, and this is true, we know it, right? Then the number of people with high education in the sample will be between this and this. Okay. So this is one example. Now let me show you another example. Let's say that we would like to select a sample from this population, but in this sample we should have at least 25% people with high education. So how big the sample should be? Of course, the bigger samples, the better, but how big it should be to get at least 25%. So what we know in this case? In this case, we still know the proportion of our population, and we also know the left boundary or lower boundary of the future interval, but we don't know the sample size. Let's work with the confidence level 99%, so we know the z-score as well. So it means that we know this, 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 we don't know this, right? And we also know that for the left boundary, we need to take z-score equal to minus 2.58, right? So that's how we describe it. So this is the proportion we expect to get, the smallest one, right? This is the proportion of population. Because it's the smallest one in the interval, we take minus 2.58. So this is, again, pi and 1 minus pi, and this is the unknown, right? Now we need to isolate n. How we do it? Well, first of all, we subtract 0.3 from both parts. So this is what we get. 0.25 minus 0.3 will be minus 0.05, right? Now we divide both parts to minus 2.58. This is what we get. Now we square both parts. This is what we get squared. And then finally we can isolate n by taking 0.21 and divide to this big number, to this small number, and that gives us approximately 582 people. So it means that if you want to get a sample with 99% confidence, this sample will contain at least 25% of people with higher education, the sample size should be minimum 582, so approximately 600 people. So you can see it's not that actually useless, right? We still can use this knowledge to calculate like a characteristic of our future sample, right? And then I have a raster up that exactly shows you how it works. It calculates population-based confidence interval for proportion, meaning we can set population proportion, then we take a sample and then see how many times this sample will be within the expected interval, depending on the sample size, depending on the other things. I recommend you to watch a short video, which will be the next one, and then play with this app, and then come back to learn how we can do the same thing, but other way around. So we know proportion of our sample, and we would like to compute confidence interval for the population proportion.